In today's video, let us understand the calculus of expectations. The valuation of financial instruments, particularly derivatives, stands at the confluence of two powerful intellectual streams: the rigorous logic of probability theory and the pragmatic realities of financial economics. To determine the fair price of a contract whose payoff is contingent on an uncertain future event, one must first possess a formal language to describe that uncertainty. This language is provided by the mathematics of probability. However, a purely probabilistic approach is insufficient, as it fails to account for a fundamental driver of human economic behavior. Today, we will embark on a systematic exploration of how financial mathematics bridges this gap. It begins by establishing the foundational principles of mathematical expectation, then introduces the economic context of derivatives and risk. This initial exploration will frame the central problem: how to determine a fair and consistent price for a contingent future payoff in a world governed not only by objective uncertainty, but also by the subjective preferences of its participants. Concept of expected value is the cornerstone upon which the entire edifice of decision making under uncertainty is built. It is more than a simple statistical average. It represents the first moment of random variable, a formal measure of central tendency that quantifies the most likely outcome of a probabilistic process, weighted by the likelihood of all possible outcomes. Its development in the 17th century marked a pivotal moment in the history of science, transforming the study of change from a gambler's art into mathematical discipline. The idea of expected value originated to solve the problem of points. This classical problem sought a fair way to divide the stakes in a game of chance that was interrupted before its conclusion. The fundamental principle that emerged was that the value of a future uncertain gain should be directly proportional to the probability of obtaining it. This insight formalized the intuitive notation of a weighted average, where the probabilities of occurrence serve as the weights for possible outcomes. For a discrete random variable x, which can be taken on a finite or countably infinite set of distinct values x1, x2, so on till xn, with corresponding probabilities p1, p2, so on till pn, where sum of all probabilities is equal to 1. The mathematical expectation or expected value is formally defined as the sum of each value multiplied by its probability. It is denoted by E of x and is equals to sigma of xi into p of random variable x is equals to xi from I is equals to 1 to n. This can also be written as sigma of xi pi from I is equals to 1 to n. This can be seen as the long-run average value of the random variable over an indefinite number of independent trails. For instance, when rolling a standard six-sided die, the random variable r representing the outcome has a sample space of 1, 2, 3, 4, 5, 6, with each outcome having a probability of 1 by 6. So if we calculate the expected value using all the information we have, we'll get it somewhere around 3.5. We can simply calculate this expected value by using the formula xi pi sigma. So this will be 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6, resulting in 3.5. This example illustrates that the expected value need not to be a possible outcome itself. Rather, it is the weighted average center of the probability distribution. If there is a negative expected value, it signifies a long-term loss for the player and the profit for the house. For continuous random variables which can take any value within a given range, the concept of expectation is extended through integration. If a continuous random variable x is described by a probability density function f of x, its expected value is the integral of the product of x and f of x over the entire range of possible values. This can be formalized as E of x is equals to integral of x f of x dx from minus infinity to plus infinity. This formulation, grounded in measure theory and Lebesgue integration, allows the principle of expectation to be applied to a vast array of phenomena, from the thermal motion of particles to the continuous fluctuation of asset prices in the financial markets. The power of expectation operator lies not only just in its definition, but in its fundamental properties, the most important of which is linearity. This property allows for the decomposition of complex problems into simpler, more manageable parts and is the mathematical engine that drives the entire framework of derivative pricing. The linearity property can be stated in its most general form as follows. For any two random variables x and y, and any two real constants a and b, the expectation of their linear combination is equal to the linear combination of their individual expectations provided they exist. The expectation of ax and by, where x and y are two separate random variables, can be given as a into e of x plus b into e of y. This property holds regardless of whether x and y are independent. This is a remarkably powerful result. For example, to find the expected value of a random variable x following a binomial NP distribution, one could perform a tedious summation. Alternatively, one can recognize that x is the sum of n independent Bernoulli random variables x is equals to x1 plus x2 plus so on till xn, where e of xi is equals to p. By linearity of expectation, e of x is equals to e of x1 plus x2 plus x3 plus so on till xn. And by linearity, we can say that e of x, this is equals to e of x1 plus e of x2 plus so on till e of xn. And this will be equal to np. This elegant shortcut is a direct consequence of linearity. Another crucial property relates to the product of random variables. If and only if two random variables x and y are independent, the expectation of their products is a product of their expectation. E expectation of x into y is equals to expectation of x into expectation of y. The distinction between this property and linearity is critical. The expectation of a sum is always the sum of expectations, but the expectation of a product is the product of expectations only under the strict condition of independence. This has a significant implications in finance. Having established the mathematical tool of expectation, the focus now shifts to the financial environment in which it is applied. This involves understanding the instruments to be priced, financial derivatives, and the fundamental human behavior that complicates the pricing problem. Derivatives are contracts whose value depends on the future state of some underlying variable, while risk aversion dictates that investors demand compensation for bearing the uncertainty associated with the future state. The interplay between these two elements creates the central challenge that modern financial theory seeks to solve. A derivative is a financial contract between two or more parties whose value is derived from an underlying asset, or a group of assets, or a benchmark index. These instruments are not claims on the assets themselves, but are rather agreements whose worth fluctuates based on the price movements of the underlying. The most common types of derivatives include forwards, futures, and options. So, let us get a small idea of these derivatives. First, let's understand what forwards and futures contracts are. A forwards contract a forward contract is a private customizable agreement between two parties to buy or sell an asset at a specified price on a future date. Because they are traded over the counter, their terms can be tailored to the specific needs of the counterparties. But this flexibility comes with the counterparty risk, the risk that one party will default on its obligation. A futures contract is functionally similar to a forward, but it is standardized and traded on an organized exchange. The exchange acts as an intermediary, guaranteeing performance and mitigating counterparty risk through a system of daily margin settlements. Now let's look into what an options contract is. An option contract grants the buyer the right but not the obligation to buy or sell an underlying asset at a predetermined price, known as a strike price, on or before a specified expiration date. The buyer pays a premium for this right. This asymmetric nature, the ability to benefit from favorable price movements while limiting losses to the premium paid, is the defining characteristic of options and distinguishes them from the obligatory nature of your forwards and futures. Now let's look into the payoff structures of some of these contracts. Let ST be the price of the underlying asset at expiration time T, let K be the strike price or delivery price. The terminal payoffs for the most basic derivative positions are as follows. First, let's look into a long forward or future position. The holder is obligated to buy the asset for price K. The payoff is the difference between the market price and the locked-in price, which is equals to ST minus K. This payoff is linear and symmetric. Gains from a rising price are mirrored by losses from a falling price. Now let's look into a long call option. The holder has the right to buy the asset for price K. This right will only be exercised if ST is greater than K. The payoff is therefore max of ST minus K, 0. This payoff is nonlinear and asymmetric. The potential gain is theoretically unlimited, while the loss is capped at the premium paid for the option. Now let's look at long put options. The holder has a right to sell the asset for price K. This right will only be exercised if ST is less than K. The payoff is equals to max of K minus ST, 0. This is also a non-linear and asymmetric payoff. The potential gain is substantial if the asset price falls, while the loss is again limited to the premium paid. The non-linear asymmetric payoff of an option is precisely what it makes both a powerful financial tool and a complex valuation challenge. A forwards contract's risk profile is directly and linearly tied to the risk of the underlying asset. In contrast, an option's risk profile changes dynamically. This dynamic risk profile means that the compensation an investor would demand to hold an option is not constant. It is a complex function of the underlying asset's price, time to cash, and volatility. This complexity renders traditional valuation methods This failure of conventional approaches creates the intellectual necessity for the alternative framework of risk-neutral pricing. To understand why a simple expected value calculation is insufficient for pricing in the real world, one must consider the concept of risk preference, which describes an individual's attitude towards uncertainty. Economists and financial theorists typically categorize individuals into three groups. The first group is risk averse people. A risk averse individual prefers a certain outcome to an uncertain one with the same or even higher expected monetary value. Given a choice between a guaranteed $50 and a 50-50 gamble between winning 100 or nothing, a risk averse person will choose the certain $50. The next type of categorized individual is a risk neutral individual. This person is indifferent between a certain outcome and an uncertain one with the same expected value. They would not care whether they received the guaranteed 50 or took the gamble. The utility function is linear, and they are concerned solely with maximizing expected return, regardless of the associated volatility. The next category is a risk seeking person. A risk seeking individual prefers an uncertain outcome to a certain one with the same expected value. They will choose a gamble over the guaranteed $50, valuing the potential for a higher payoff more than the certainty of the smaller one. Their utility function is convex. The prevalence of risk aversion among market participants has a direct and profound consequence for asset prices. To induce risk averse investors to hold risky assets such as stocks, these assets must offer a higher expected return than assets that are considered risk free, such as the government bonds. This excess expected return is known as the risk premium. The existence of a risk premium means that expected future price of a risky asset is not simply its current price compounded at a risk-free rate. Instead, it is compounded at a higher rate, mu, which incorporates both the risk-free rate and the risk premium. Thus, in real world, the expected future stock price is given by E is equals to S naught into E into mu T, where S naught is the initial price and mu is always greater than R. This single fact lies at the heart of pricing dilemma. If one were to calculate the expected payoff of a derivative using the real world or physical probabilities that lead to an expected return mu, what discount rate should be used to find its present value? It cannot be the risk-free rate R because the derivative's payoffs is itself risky. It must be some higher risk-adjusted discount rate K, which is greater than R. However, determining the correct value of K is exceptionally difficult. It would depend on the specific riskness of the derivative's payoff and the aggregate risk preferences of all market participants. This intractability motivates the search for a new valuation methodology that can circumvent the need to estimate either the true expected return mu or the appropriate risk-adjusted discount rate K. The challenge of pricing derivatives in a world of risk-averse investors where true expected returns and appropriate discount rates are unobservable led to a conceptual revolution in mathematical finance. The solution was not to better estimate these unknown quantities, but to sidestep the problem entirely. This was achieved by constructing parallel artificial risk neutral world, a mathematical fiction where all calculations become remarkably simple. The genius of this approach lies in demonstrating that the unique arbitrage free price derived in the artificial world is the correct and only possible price in the real world. The conceptual leap required for modern derivative pricing is the recognition that there are two distinct types of probability measures used in finance. The first one describes the actual observable world of forecasting and investment. The second is purely mathematical construct designed for sole purpose of pricing. Understanding the distinction between these two, the physical measure P and the risk neutral measure Q, is the key to unlocking the entire framework. The physical measure, often denoted as P, represents our best attempt to describe the actual likelihood of a future event. These are the probabilities one would use for forecasting economic growth, managing a portfolio's long term risk, or making a speculative investment based on a belief. The probabilities under the P measure are typically derived from historical data, econometric models, and subjective analysis of market conditions. A defining characteristic of this measure is that the expected return of a risky asset, such as stock, is its true real world expected return, mu. As established previously, because investors are risk averse, this rate must contain a risk premium, meaning U should be greater than R, where R is the risk-free rate. So, in simple terms, the P measure describes the world as we believe it. In contrast, the risk neutral probability measure, denoted as Q and also known as the equivalent martingale measure, is a theoretical construct. It is not intended to be a realistic model of the future. Its purpose is not the prediction but the pricing. The Q measure is specifically engineered to simplify the valuation in a world free of arbitrage opportunities. The single defining property of the Q measure is that under this artificial set of probabilities, the expected return on every asset in the economy, including risky stocks, is precisely the risk-free rate R. This implies that if we discount an asset's price process by the risk-free rate, the resulting process is a martingale under Q. A martingale is a stochastic process for which the best prediction of its future value, given all the information available today, is simply its current value. In financial terms, this means that the discounted stock price follows a random walk with no predictable trend or drift. The Q measure is not independent of the P measure. It is mathematically derived from it through a formal change of measure. This transformation, described by Radon-Nikodym theorem, essentially reweights the probabilities of future states of the world. The transformation works by systematically reducing the probability of good outcomes and increasing the probability of bad outcomes relative to the real-world probabilities under the P measure. This adjustment is calibrated in such a way that it exactly cancels out the risk premium. Consider the valuation problem again. Under the P measure, the price of an asset is expected value of its future payoff discounted at a high risk adjusted rate. Therefore, we can write V naught is equals to EP, or the expected value of the payoff, into e to the power of minus kt. Under Q measure, the price is the expected value of the future payoff calculated with the adjusted probabilities and discounted at a low risk-free rate. Therefore, here V naught is equals to EQ payoff, or the expected value of the future payoff calculated with the adjusted probabilities, into e to the power of minus RT, where k is greater than r. The magic of the risk-neutral framework is that both formulas yield the exact same price V naught. The adjustment for risk is simply shifted from the discount rate to the probabilities themselves. By construction, EQ of payoff will be lower than EP of payoff, and this difference by the fact that e to the power of minus RT is larger than e to the power of minus kt. The framework does not eliminate risk or risk aversion. It simply repackages it into the probability measure, making the subsequent calculations far more tractable. With the distinction between the physical and risk-neutral worlds established, the central pricing problem can be stated. This principle provides a universal and elegant formula for valuing any derivative security in an arbitrage-free market. It represents the culmination of the conceptual shift away from the subjective expectations and towards a pricing framework based on replication and internal consistency. The fundamental principle of risk-neutral valuation asserts that the arbitrage-free price of any derivative security at a time t, denoted by Vt, is equal to the expected value of its future payoff at time t, or capital T, denoted by Vt, where this expectation is calculated using the risk-neutral probability measure Q, and the result is discounted back to the time t at the continuously compounded risk-free rate R. Therefore, V small t can be written as the expected value of V capital T into e to the power of minus R capital T minus small t under the filtration Ft, where the filtration Ft denotes all the information available up to time small t. This formula is the cornerstone of modern derivative pricing. It elegantly replaces the tractable problem of determining an approximate risk-adjusted discount rate with the more structured mathematical problem of identifying the correct risk-neutral measure Q. One of the most profound and often counterintuitive consequences of the risk-neutral valuation framework is that the price of a derivative does not depend on the underlying asset's real-world expected rate of return mu. An investor's personal belief about whether a stock is poised for a spectacular growth or is likely to stagnate has absolutely no bearing on the correct arbitrage-free price of an option written on the stock today. In the risk-neutral world, all the information and assumptions about the asset's real-world drift mu are discarded and replaced by the risk-free rate R. The pricing formula depends on the current stock price, its volatility, the risk-free rate, the strike price, and the time to expiration, but not on mu. This is a radical departure from the traditional asset valuation, with the expected growth rate as a paramount consideration. Using the calculus of expectations and risk-neutral pricing, we derive many mathematical frameworks for calculating the price of the derivative at the current time. We have discussed some of the frameworks like the binomial option framework and the Black-Scholes framework in previous videos. Despite its limitations, the risk-neutral framework represents one of the most significant intellectual achievements in the history of finance. Its development provided the theoretical foundation for the exploration of the global derivatives market, which now has a notational value measured in hundreds of trillions of dollars. The elegance of the martingale approach lies in its ability to distill a complex economic problem, valuation under uncertainty in the presence of risk aversion, into a tractable problem of finding an equivalent measure under which discounted prices are martingales. It demonstrates that, for the purpose of pricing contingent claims, we can act as if the world were risk neutral, not because it is, but because the constraints of no arbitrage forces prices to behave in a way that is consistent with this artificial construction. This powerful insight truly bridges the disciplines of probability and pricing, creating a calculus of expectations that is fundamental to the theory and practice of modern quantitative finance.